Okay. And then the floor is yours.
Thank you. Make sure we come. Oh. And
I think, no, I think it's half of the farm board.
just say like two
Oh.
words.
Oh, okay. Well, you have a view and I have memories, which is not really reliable.
Okay. Yeah, I'll start by drawing some picture and probably further put some picture coming.
Okay, yeah, amazing. I'll see.
So I'm gonna try to share what I've learned really MIT course on generative AI, and I'm gonna talk about two things: sampling and full score matching. So broadly, what a generative AI thing does is that you feed it with a bunch of data from, say, let's say you feed it a bunch of dog pictures. Implicitly, the collection of all dog pictures, not just the sample you'll have, is a probability distribution on some background space, like the space of all pictures that display on the screen. So the job of this AI system is to predict what this probability distribution is from the sample of dog pictures that have been given. And then once that's done, try to generate samples from that underlying distribution. It's generative AI. So the first problem is known as learning. And the problem of generation, once you already know what the distribution is sampling. So today I'm going to try to do things in reverse order, sampling and then the learning. Partly because sampling is, in a sense, easier because it doesn't rely on data set. You have the God's eye view of the distribution in that. So the way we try to do this is that, let's say we have some desired distribution. We already know what the data distribution is, and we that as a key step. That's our first objective.
Hey, glad you're here.
So I'm just going to talk a bit about flow and score matching and sampling generative AI, and I'll try to remind us at each step what we're doing. So this is inspired by the animation you showed me, except I'm too lazy to draw 16, so I just drew 4.
Oh, no.
And some starting distribution that is easy to sample. Let's say just the Gaussian distribution of mean 0 and variance 1. And the idea of this whole setup for both sampling and learning is to set up some kind of ODE or an SDE, such that if your initial condition x0 is distributed according to your noise distribution, the one that's easy to sample from, then you run this guy through the PD, the SDE, and at the end you get x1, which if you set up your equation properly, this should now have the distribution E star. And well, back to our set, U sub t is a drift. and xt is variable. And let's say xt is some d-dimensional vector.
So the variable u and sigma are varies along t.
Yes, that's a great point. The drift is a function of t, and the flow, the drift, is also a function of t. So it's this drift you can think of as kind of time variable. So how do we do this? I mean, this distribution can look super rough, arbitrary. It's not clear at first. The way we do this is that we first pick some point in the target space. Let's say this point. We figure out a way to flow from this probability distribution to the Dijak distribution centered. And later on, we try to find some way to average this process according to the distribution P star. And once we smear out that, it should give you what you want. So we can first try to engineer a probability distribution, a family of index criteria that interpolates between the standard Gaussian and a single point. And the simplest way that comes to mind is to just shrink the standard deviation linearly. That is, if we denote the distribution of xt by p sub t, then we can engineer p sub q be the Gaussian. Well, we have to actually shift the mean too from 0 to 0. So the mean would be p sub t. And the variance is shrinking. And since we're shrinking the standard deviation linearly, we have minus squared. Yeah. So now we have a probability path, and it remains to find the u sub t such that this equation gives me that probability path. Well, first thing to observe here is that, oh, this is cut off. Oops. The first thing to notice here is that we can explicitly engineer a solution to the equation that satisfies this probability path. Namely, we can set xt to be, let's see, t is well, that's still t. Was the noise of magnitude 1 was dampened by 1 minus t, 1 minus t. X stop. So now we have a solution to some equation, and we're trying to reverse engineer the equation from that solution. So we want to find what ut is from this. And the first thing we can try is, well, let's just differentiate from hell. So we have to differentiate this. C plus minus it's not t. And we kind of want to get rid of this initial condition x naught from the equation. So we back substitute x naught from this equation in. And at the end, we arrive at the equation equals minus 1 minus. This is just an algebraic substitution. So now we can simply let u of t to be, well, u of t of some argument, say x3. It's just within the minutes over 1 minute. So now at this point, we have solved the problem of finding an equation that flows from Gaussian 0, 1 to a direct point distribution. Now comes the process of smoothing. Before we do that, we want to identify everything we've done with a parameter z you have kind of abstracted away from the notation. So let's rebaptize things. Let's say we define well, so far we have piece of t, which implicitly depends on t on z. So let's change that to includes the in the notation. And this notation is somewhat suggestive of condition. And similarly, we change u sub t to u sub t condition on z. And now we first try to construct the probability path. P sub t. For real this time, and this one is the objective distribution instead of this is the dot distribution. We try to construct this probability path from this. Well, if we let z be distributed according to p star, then we can just average the dot path according to this distribution and end up with the path that we want. That is, we set pt to be the average of existing. Let's say pt of x, where x is us. This is our existing dot path, averaged by the distribution of the. You might also recognize this as obtaining. Well, if you think of p sub t, this notation here as a conditional distribution of x given that can end up at z. And you think of p star as the Martian distribution with z in the joint distribution of x and z, then this actually gives you the Martian of x. So now we have a path. We still need to find what u2 is. For this, we revisit Fokker-Planck division. We're almost up. Yes, that's. So recall Fokker-Planck equation. We have some SDE of this form. And where p sub t is the distribution of x sub t. Then the equation describes how this probability path p sub t evolves in terms of the drift. In essence, it relates the drift with the probability path. And it says that we should take the time derivative of the probability path. This is equal to minus the divergence of the product, the probability, and the drift plus the diffusion term, which is this one. Divergence of gradient of piece of field. And it's worth clarifying here that the operator is gradient and divergence apply to the collection of variables x. I say collection of variables because x is actually a vector. And this derivative pertains to the variable t. This is what the equation says, and for now, we are just working with an ODE instead of an STE. So we ignore this term. And this equation immediately gives you a way to reverse engineer u sub t from p sub t. And here's how to do it. It's just the left side Fokker-Planck equation. And by the way, this Fokker-Planck equation without the diffusion term is sometimes known as a continuity equation, which you have mentioned in your talk. I'll just use the composition. This integral is on variable t. Sorry, on variable c. This derivative is on variable t. Now, this inside looks a lot like left skin side of the Fokker-Planck equation. So this is we're just looking at the path condition on z. You just copy down the right hand side with the condition on z and on whatever is x. Yeah, integral is with respect to z. Divergence is with respect to x. Now we introduce and then disappear a term inside the key. Actually, outside. We're going to merge with p sub t of x and then cancel it out this with it. I just break this. Why did we just introduce this extra term? Is because we want the inside of this divergence to look like this. At that point, we should just call this subgroups. So yeah, in some way this derivation just gets passed in the equation through this decomposition. So right now, this already resolved the problem of sampling entirely for flow-based models. That's a fancy term for models based on ODE instead of ST. The way we do it is withdraw some sample from normal 0, 1. That's something we can do. We pass through an ODE with this drift term, and then we end up with a sample drawn from P star.
I'm sorry, I really like that. I'm gonna steal that. the flow-based models are a fancy name for an ODE rather than an SDE. You have decomposed the market. Deconstructible.
I mean, it's actually kind of inspired by a discussion previous to this during our past meeting about instead of saying learn, say comprehensible.
Or estimate, yeah.
Yeah, yeah, drift flow. I mean, there are even some of them say.
So I was saying that the problem we want to solve in sampling is essentially solving the draft turn with SDE.
Exactly. You're trying to reverse engineer this equation. This equation is. And now we have an explicit expression of U of T in terms of the in terms of the target distribution to solve. So now we can do flow-based models. How about score-based stuff? That's the next for SDEs. And in this case, we use the full quantum equation with the diffusion term. And we understand this picture well enough in this.
Oh, one second, can I ask, like, what's the definition you put on the PT conditional Z? Yeah,
This is a relabeling of the PT we've obtained when the target distribution was just the Dirac distribution on this. Previously, I did not include this individualization to avoid clutter. But now, because the whole is based on the Dirac, it pertains to parameters in this way back. We're doing things more general.
what's the difference of the PT over there and the explicit form of the on the graph?
This I should be able to again press. Issue on the
Oh, so that's like an example of that.
Yes.
Okay, I'm gonna ask some like really kind of bad questions. So doesn't this do like the task that you want optimal transport to do?
Let's see. I haven't really thought about.
Yeah, the flow is the optimal transport.
Well, I don't know that it's optimal, but like it is.
It is a way to transport, yes,
It is optimal. I mean, I don't know that, but like, I guess I'm asking like if this is the way. This is like a. But you have a method to transform one, like flow one distribution to one. So like, I guess like, my questions are like. I don't really care if it's optimal, but like, why introduce the random stop points? If you already have the way. I don't know.
That's actually a question that I've been thinking about, and I don't yet have to really get a satisfactory answer. The question is essentially, why do you do score matching and SE based models?
Well, score matching came first. So it was the Sun and Eman paper in 2019 that introduced score matching. Flow matching was an improvement that Lippmann made in 2022. So we started with score and then got flow. You know, and the question, you know, the paper that Leo presented last week, so well, you know, claims a lot of advantages for flow matching, but it's not, or I wasn't able with the pictures that I did to like absolutely show that flow matching was better, but like that's where we're sort of, I think that's where the literature is sort of going.
Because it is something like. Because the randomness just like more easily computable.
I don't think that the randomness makes it more easily computable. I think that it was more intuitive to think about for Sun and even the guys at Google that invented this, because they were thinking of the paradigm of noising an image and then denoising it. So they were going to they were going from P star to a Gaussian, right? So they thought, okay, well, how do I do this? I want to add noise to it, like a Markov chain and get an invariant distribution. The invariant distribution I want to start with is the easiest one, the Gauss. And so like that was the way to think about it. And so, they coded what they thought. And then I think Lippmann said, hey, like, let's just deal with the transport plan, which is the flow. And I mean, I'm like intuiting, I'm like applying my thought process
Yeah.
to them. I don't know that this is what they would say, but I think that was what he did and said, oh, wow, not only do I not only do I reduce an SDE to an ODE, but I've got better numerical properties. And then the CAC flow was yet another not insubstantial improvement. But yeah, but that's my speculation.
That reminds me, I've been reading some other stuff and there are quite a few different conventions, like some people use reverse time and go against thermodynamic wisdom and using forward time. Also, in a lot of stuff I've read, you have a process that has an equilibrium distribution that is noise. This process, I don't think it has an equilibrium distribution, and you reach your perfect distribution in finite. After this time, probably just and divergent.
Is this? So I never read, well, I know in the spring, it's like. Mr. was talking about the displacement calculation stuff.
And lots of things.
He said, I think the word displacement interpolation. This spring, you guys remember this? I'll be honest, I didn't read it, I didn't really read that much, but I was just wondering if this is the same thing.
He talked about like the invariant distribution.
Yeah, these were like, this was in the list of potential future topics. We never.
Oh, okay. Yeah, I'm sure whispering beyond the reach of Zoom, I'm sure I was so overwhelmed with the basic material. If there wasn't a homework problem, I was buried with that.
Can I ask one more question about like big picture? So here is like, we have a target distribution P star.
Yes.
And the Gaussian distribution is that, is that we want to peak, or it's like it's given we have to do this. Like the initial distribution.
In principle, you can write any distributions or initial, but there are some reasons why the Gaussian was chosen. It's, for example, it's very easy example, but we can sample out. It's not right. Point is that the Gaussian distribution has that right exponential density that gives you clean expressions when you later on do score matching. So score log density.
And the goal of this problem is that we want to sample the P star.
Yes.
Oh.
And your computer can generate a sample of say normal 0, 1, but how do they could spit out distributed so.
And then we can find a probability flow from our initial to the target, that is PT defined over here.
Precisely.
Okay.
In this case, restricted to the round signal, but once we smooth it out.
So directly is kind of like we know from the distribution of the star, right?
But right here is an arbitrary point, and it's an arbitrary point. It doesn't compute the point P star, and that's what makes computing everything conditional to be tractable. It does not depend on the stipulation of later on later words.
Then can I ask like where's the Dirac come from?
Well, Dirac distribution is just kind of the simplest distribution on the road.
And then like I guess like why do we also have like a x0 to x1 and then like SDU or like xt? Like if we already have the probability flow PT, like why we also want to SDU.
I see, because we can have the problem flow. But how, for example, if you want an arbitrary, I say it's kind of equals one. You have the form of density, but how do you tell if you have the sample from?
So, okay, to actually sample it, we need to solve the SD over there and especially the draft term. That,
Yeah, that's the goal.
Okay.
To transform a distribution into.
um,
In one dimensions might be, what the inverse be affected. Something that does the same thing, but higher dimensions.
and here we use the continuity equation that connects the probability flow to the draft term, and then we can eventually solve the draft.
Exactly.
Okay. Thank you.
And like, if I'm actually on like that images game like Facebook. P star has some. And what sort of distribution is it?
Let's say if we're interested in generating dot pictures, then P star is it's kind of, it feels almost more philosophy than mathematics, but the distribution of all dot pictures in the ambient space of all pictures.
And like, am I starting from still like a Gaussian distribution?
You always
So-
start the easy example. Actually, going back to your question of up and down with this sort of plan. I think it's generally not, correct me if I'm wrong, but I think it's generally not optimal in the current orbit sense because. And OD does not let you split a plane and send it to multiple places.
Because it's not, the mirror. I'm sorry, remember in the spring, then you went over Betamu and Renier and the Rockefeller, and like it had to be monotonically cyclical in order for it to be optimal. And I don't think there's anything in this that where you would have points crossing each other. So I don't know that it's not an optimal transport plan. There's nothing in the vector field that's like a cross. Or so. I mean, your thing is, well, if I have the normal distribution and I move it to one point, I can't split the points, but they're all going to one point at this point, so I think. I suspect it's optimal, but work.
In the restricted sense, I would be not disappointed if a lot, in the general sense. I'm thinking about your transport plan as the company, the distribution is normal, right? And generally you can allow this couple having arbitrary form. Which here it seems to restrict this one sending a point to it. A deterministic point seems to put a restriction on what form is covered. But the question still remains if you consider this problem distance language where you do restrict this. Is optimal. I don't know. It's the problem.
How do you define like the cross function?
That is a good question. Yeah, what's the most natural cost function?
It's usually x minus y squared.
Right, the squared symmetry.
Yeah.
About author studies.
Sure. Well, the metrics are on the state functions. space. Open things to think about.
We'll break our heads on this later. Keep going.
Sure, no, thank you for these
Very good
questions.
question.
I'm actually still in the process of typing up the lecture notes, and the reason I haven't sent them yet is because I want to incorporate broader comments here into them. So this is great. So we have already solved the sampling problem for ODs, and it's just a quick extension to do the same thing for SDs. We again use the Fokker plant equation. A piece of notation I should address before writing. Since we're working with an SE, there's no guarantee at all that drift will be the same as the drift for OD. So in the context of an SDV, I will change the notation to make it drift V instead of V. And we will try to express V in terms of U because U already have an expression. So the first thing I'm going to write down is still within the flow-based version. Now this U is the top. And we want this to be the same as what we get in the score-based version, which according to the Fokker plant equation is that's the Fokker plant equation. And now what we do is just compare terms. You want to isolate what the V sub t is, so we might as well just move it outside. And nice graph this graph board.
Yeah.
I'm just gonna isolate this term. So if I guess this. Here, and this term is moved to the side. And now we wrap up the divergence package. And at the same time, let's factor out. So we have minus divergence of PTX, VTX equals the minus divergence PTX. This thing is going to be. And you can actually clean up this expression a bit more. VTX is the same, but when you have gradient of piece of P over piece of chain rule, that's all the diffusion is. But this becomes gradient log. And this guy here is known as the score function. So we can now express V as T in terms of use of T, which we have on the board, and in terms of this thing. Well, since we're doing something, we already know what the distribution P star is, therefore we know what use of T is, therefore we can compute this. But when we're doing learning or estimating later on, this is actually an additional parameter that we still need to work. We need to match. Is why it's called score matching.
I probably didn't know this. If we do P star, then I don't.
So if you knew P star, you still have to find where to sample it. Right now, we're just trying to find where to sample it. It's a bit confusing because the normal order of doing things is the learn and then sample. But for this presentation, I'm going to first sample and then learn. And in order to sample it all, I have to assume you know what the target distribution is. In practice, it's probably you're instead of sampling from the target distribution, you'd be sampling from some estimate of the target distribution based on what you learned in the given data set. And it's worth noting that as before, we had the decomposition of the drift use of in terms of the condition on Z. We have something similar for the score. Okay, let's try this word. So score. Reverting the chain rule. And now we decompose in terms. Usually this. We break up the partial. Integral with respect to Z. Gradient with respect to X. And now I'm going to inject a hidden term into this thing. And now you have gradient probability over the probability itself. This is a score. And you might recall from before the decomposition. So if that's. I was able to write this down without consulting the notes because they're the same thing. If you replace G6 with score, everything else is the exact same.
Is a U of T the same thing that we derived before? It's like we just mainly,
This is the UT that we gave the formula for.
okay, the same one.
Yeah, before that, we recall that we started with finding computing the conditional drift on Z because it's easy to transport normal distribution back to a single point, and then we later smooth things out. And this describes essentially the process of smooth. And this describes the process of smooth out the unconditional, the marginal usage as some kind of smooth of conditional. Yes.
Still feels like averaging it.
This is the average performed on the level of the probability path. And we use upper bound condition to try to turn this to pass from this kind of averaging the level of probability paths to the level of drift. And the fact that these two formulas are the same becomes very, we're trying to learn things. More on that later. This right now concludes the section on stuff.
Can I ask a quick question?
Yes.
So, like we did kind of like two cases, like first OD, then the SD. Like, can I say like for the OD case, it's because that we sample from the Gaussian and they would kind of plug in the form of like the solution of XT. So we plug in it, then we have something that's have a 0 for the sigma for the diffusion. That's where the OD comes from because like we're plugging and then the sigma is 0.
Yes, and all these special cases of SD diffusions.
But then why do we have like the sigma not equal to 0 in this case for the SD?
So the question, why do we also use the SD regime?
Yes.
Or capital regime? That's a question that I've been wondering and don't have an answer. I've tried consulting with ChatGPT and says anything about like sometimes just having the extra of randomness when you explore and for certain distributions. I don't have anything to like.
Because it seems like very solid to me, like when we do the OD case, like we can explicitly plug in the solution of XT, then we would have like sulfur UT, which is exactly some form, and then we don't have a term for the diffusion. Yeah, that sounds very solid. So I'm just wondering.
Yeah, why do we even do this? You mentioned that low matching, the OD version, that's the version. I wonder why people still do the SD stuff.
Well,
I could believe that like putting it in random space is more stable. Like even though the OD version is cleaner, like I could definitely believe.
I can imagine, for example, if you're trying to do gradients or whatever, you get stuck in local if you do those problems. If you do it random,
That's a good example.
So now we move on to score for match. I'm going to raise everything. That's
Wait, can I ask one thing? Like, so can you say again in plain language what P17, like the integrand of PT is? Like, yeah, plain language of that.
this is the probability density you get if you try at time t, if you try flowing from the normal 0, 1 distribution to the Dirac C distribution.
So like. What properties does this thing have? So is it like so. So what I know about this function, what it is at like P0 and what it should be at P1.
Yes, this is. Yeah, this is actually really the only. The only salient part of this. We want P sub t to be Gaussian at time 0 and the perfect distribution at time 1. And one can verify that this expression indeed satisfies. Because let's say for at time 0, doesn't matter what the c is, you start with a Gaussian density, and you're just integrating that Gaussian density out with respect to something unrelated to it. That just returns you the Gaussian density. And at time t, this piece of t just becomes Dirac C, and you smooth the Dirac C over the distribution of the star. You can go this. All right, Lorentz score matching. Previously, we've done all the sampling work, assuming we know what P star is. We actually don't, so we find some way of getting to it. And instead of trying to approximate P star directly, you try to approximate in full matching, you try to approximate U sub t. Because as we've seen, U sub t and P sub t and P star gives you really an equivalent amount of information. If you know what P star is, you can engineer U sub t. And if you know what U sub t is, you can construct the equation and use that equation to flow from Gaussian to P star. So the relative is
So the focal point between.
yes. And another nice thing about trying to approximate U directly is that if you try to approximate P star, then you have to redo all the sampling work. But if you approximate U directly, you bypass all that work and you already arrive at the right drift for performance. So here I'm going to introduce black box neural networks. I don't quite know what it is, but let's say U sub t is what we want to approximate. Want to find U sub t. And
I should work this for my real analysis professor back in the
and we're gonna call an approximate to this U sub t superscript theta, where theta is some set of parameters that describes the object sub t. How you do this parameterization, I have no idea. I looked through the code and still don't quite understand. So I'm just gonna leave it there to say you can do this perspective. It's a set of parameters that we can try to perform optimization. And we need to define the notion of distance or loss function between your approximate and the true value. And let's call this, as we're doing full measurements, this F of D of the parameters. And this is going to be an average in some sense the square. This. Where do I want? It's also the mean square error because mean square error.
That's an expectation or?
Yes, that's an expectation. I have not specified over what.
And these UT root and whatever, like the same space that X used.
In terms of populating spaces.
Yeah. This is, well, this is the,
What?
this is the transport plan. You're trying to learn the transport.
Maybe things
Estimate, excuse me, estimate for transport.
I'll try to describe what the expectation is over, or maybe that might help answer this. So the average error, average in what sense? Average over time and over space. Time. There's the default is all kinds. One. And X. The half distribution. P stuff. This is kind of a clear part of this.
Be the RV flow.
P is the probability that's at some given time, and in this case, the time is right. Right. Uniform right here is true.
Why am I choosing random time?
You just want to quantify the average.
Oh,
And there is a really nice way to sample this, which is first sample some other Z to be distributed by 550. So this you can kind of do when you're learning because you're given a bunch of pictures which are assumed to be IID samples. So and now I'll use sample X. Condition. And the next way about this representation is, as before, we saw if we don't condition on Z, that is, if we're trying to calculate the smooth version of something, it depends on the target distribution, which right now we don't know. But the moment you express it in terms of a marginal, it becomes tractable. If you know what this marginal is, once you sample Z, this can calculate quite easily. This doesn't under information.
But we also have like the equation rows, like you express it, you by the margin, by the integral of marginal over the
Yes,
star.
and that density that you're trying to integrate with respect to that's
G star. It's unknown.
that's yeah. But turns out what we're trying to do is we're playing the randomness. We're playing that unknown somewhere else in a way that is not, we're playing the randomness in the sample and do it out in the sample. On the between. And that raises another problem, which is the problem of this expression. This is just that no. This is marginal, it's not conditional, so you don't know what that is. Let's just do the most naive thing and define a new loss function. Which is going to be the exact same thing as this, except we add this afterward. And this called F sub C because C for condition. And this is a much more trackable expression, it's recognition. Basically, these capital.
Do we even know it's related to calculator logic? Like, doesn't it make sense to try to minimize with respect to this loss?
And the amazing thing is that these two loss functions differ by a constant. Their difference does not loss. And it's not too bad to actually show this. Let's just compute the differences. F we're just going to expand both squares. We're going to square this thing, FOIL this guy too. At the end, this u theta t term and this will both get squared. And because we're subtracting, they just go away. What do not yet go away are two differences. The square of this and the square of this. And the cross terms we flip, which is T here for transpose. Yeah, different symbol for transpose. Maybe take that. I just realized on tech, this transpose T looks very different from this big T, but when you try to write it. I don't want to use star because star is taken up by the object density. So I'm just going to use dagger, and I don't think, yeah, we're not looking at the positive part of anything. This is not too confusing issue. So visible? Yeah. Okay. So we have this term, and these cross terms. What's going on up here? I don't see a theta, so this is a constant. That's good. How about this guy? These guys do depend on theta. And it turns out that this thing and this thing are the same, and they cancel out. I guess right. So are we convinced that right now we just need to show that these two guys cancel out in order to show that?
That they only differ by a constant.
Yes.
Yeah, I'm convinced, but I'm not convinced. I am not yet convinced that those two things are equal.
I see, we will show that. And I'm going to, if we're okay with everything we've done so far, I'm going to raise this part of the board and copy this down and more of it. Okay. Sounds good. So here's one thing that we're trying to cancel. That's one thing that we're trying to test.
And we extend this expectation in terms as an interval. So there are three variables, x, z, and t. The integrand. Story is now. This is just a joint density of the three variables. And you can rewrite this joint density as first example two, and it's uniform, it's this one. And you can sample this zero. Which has this the P star. And now you sample X, which now you know what Z and T are. The density of X is this because of this alternate method of sample P, sample T, and X. We can come back to your question. Try to put these. I will slightly rearrange order information. Yes, here. And now observe that this guy here does not depend on Z. So we can actually swap looking for it outside the Z. And once we've done that, we can actually introduce another hidden term. And now things should look a bit. This is exactly the composition of UT unconditional in terms of this condition solution. So it's both of the surface. Right. And it's piece of here. This is the joint density. Entity.
So in fact, we have recovered.
This is the other thing that comes with the chess biology.
Yeah, and we can. So at this point, we have shown that the conditional and unconditional object functions are different by a constant. So this is the objective function for flow matching. We still need to deal with score matching. And turns out we've already done most of it.
So we're good with the flow matching vision.
We have written down the object, a tractable object function for flow matching, which was useful for that subsume, which was untractable. We've written down the objective function and we're gonna outsource the problem of actually optimizing it to doing neural networks. So how can you describe how to parameterize things in terms of theta?
Right, exactly. That's what I wanted to ask.
Yeah, right now it's just a black box. Neural network,
But it's like something we know, right?
Yeah.
something
We don't worry about.
that you can do inference.
Okay. I take it.
Yeah, it's a bit unsatisfying, but this is all I.
Yeah, but like, even just organizing this into the lecture notes. So that we can like aim ourselves at this, I think is value add. Cause we, you know, like. We can fill in the details on the neural network, and then there's. Like a source for this that isn't like referring to all of these different papers. That's value add.
Actually, yeah. Another reason why I was gonna type up some, I was making some notes, is that the notation app this here is different, a bit different from the notation we used in the document that was in the lecture notes that I was reading from. And I find this just a bit kind of weird right now.
Yeah,
And so like we do make those at night. So correspond these issues. This is great. Thanks. I really tried to make things as clean as I could. But still there. Superscripts, subscripts.
Yeah, and I feel like the marginal to the unconditional method, it kind of, the idea is like using like frequently in about computer as well. But yeah, that's how we go from the one dimension to high dimension. Still, we go try to figure out the formula for the marginal, and
yeah,
then reconstruct the unconditional. Yeah, kind of follow the similar path.
Well, it's a nice idea. You do the simplest case, which is one to it around. Okay. Back to score matching.
so I'm sorry, but one other thing. Do we have a server that we have access to? We could actually program this up. Since I went to Peter Boyd. And you know, Dr. Francis said he goes Anthony Cruz in the stats department, but I didn't. Do you guys know if there's like a server we can get on and like actually write up some Python code?
I know the stats department has like three different clusters. Like I know they exist. How easy it is to get access to them, I don't know. Probably if you say it's from cluster.
Yeah. And do you know who runs those clusters or what?
Gosh,
Okay,
sorry.
all right, good.
Do you mean that the Python code is kind of like train the neural network?
Yeah, I mean, I wanna
There's
like,
a
I wanna actually like get some pictures, I wanna make doggies and trains and
Uh-huh.
planes and, you know, like. See this work,
I looked at the labs, I got kind of stuck at neural network there. It's actually
yeah. And there's a whole area that's hot now in probability of like. When you say train a neural network, what does that mean? Like you generally can. You know, it's like a gajillion parameters. But you can generally like. It sits on some manifold that is, you know, usually much simpler to write down. And so, you know, that'll give us a lot more insight. But these notes are, your notes and these notes are gonna be a great solid.
We can talk about like how we can implement
yeah.
training neural network.
You know, I mean, I think that like, you can just explain this in reasonable terms. Is useful if we can like turn it into code and talk about which one is useful, that's probably some kind of a contribution.
Yeah, definitely, and definitely.
You know. There's a lot of time on that.
Score match, right? We define similarly an unconditional and conditional false function. For a score match, I guess. And the approximate with or lit with us. Approximate split. I guess right. And the condition. And what's the natural guess here between these two objective functions? Constant. The different variables, again, and you prove it by the exact same argument. And the reason why this works is that really the pretty argument, which is the composition of U sub t instead in terms of U sub t condition holds for the score as well. For the score, the composition formula, it's the same formula. Previously over, yeah. So using the work. I am almost finished.
And the ST is parameter theta is seen by some neural network we can get access.
Yeah, there's this. Yeah. And right now it's like we're doing a lot of extra work for SDs. In ODs, flow match, oh, that's it. But for SD, you have an SD flow V sub T. And this extra thing. Score, and somehow have to approximate both. And it turns out that if you approximate the score, you also get the drift. Yeah, the drift of VT will refer to in terms UT and score. If we know the score, also get VT from it, and then get VT. And here's how we prove it.
Oh, now there's something confusing about how the score came before the flow, because usually when you're like getting the relevant stuff of the score, you already have to get the stuff for the flow.
Yeah,
Like it's,
Yeah.
well, I guess I don't know if like the rationale it was like this, I don't know if this argument came after people already knew it. Flow was.
Flow is vapor.
Yeah,
yeah, it's.
Oh, no. I'll try to the right. Well. School. And here, the advantage of choosing the Gaussian distribution to be the sound, to be the initial sound. We first try to express conditions, right? And conditions. Let's break down exactly what they are. So the condition with flow, we have way back. We have calculated this to and what's the condition score? This is an exercise in differentiation. You have a Gaussian density. Take the log, base one comes down, and we're gonna take the gradient. We're gonna take the gradient with the square root term attached to the disappears. And try to plug it in. So then that gives. Split. And for this reason, we can express. We're going to add in t term on the top and the bottom. And then split this up. And split this up and at the same time add a plus and minus.
Now whether it's the same top. Minus.
And this is starting to look like this.
And except that we have an extra here and one less, one minus here on top. So this is like the one minus over here. The conditional score. Plus, there is on the top of this x times 2, so this ends up with this. This is how you express the condition for the conditional score.
And to get the overall Marshall stuff by more or less the same speed. So recall the composition. We've set this.
And now we're going to substitute in this guy. Or you can substitute. I'm gonna actually, once we perform the substitution, I actually expand the whole interval. Right. You just need to say them throw over these two coefficients ended up here. And the score ended up here. Yeah. So here, let's go to the first term. This is exactly the composition of the full score in terms of partial score. This is. And down here. This is the decomposition of the unconditioned of the condition. So this integral becomes p sub t s. These guys are gone. And absolutely. It's the same formula as what we had for the marshals. Of expressing the marshal for marshals. So once you know the score, once we have the score, also the score. And that's all I created here.
That's awesome. Thank you. I can't wait to see those.
I'll try to get them done by tonight.
Last. Just like we can always do this, like, low mention, score mentioning, based on the dates we have.
Yeah.
Like the marginals are interchangeable, and unconditionals are interchangeable. So you get good, but.
We both want top of one. So we gotta get, so, all right, let's turn this off and then, because I'm not gonna mess this up. We gotta get one of the kids upstairs to take a picture of the four of us with Pablo.